All right, so today we are going to be talking about balanced three-phase circuit analysis. And we are going to kick things off by looking at a YY circuit. So let's start with this. We have a Y-connected three-phase source. Down here will be our neutral. So this is going to be lowercase n, lowercase a, b, and c, so that we have phase voltages VAN, VBN, and VCN, like so. So this is our source side of our system. Over here on the load side, we are going to have a Y-connected three-phase load. Which is going to be composed of three impedances. We'll have ZYA, ZYB, and ZYC. And connecting our source to our load will be our transmission lines, which are characterized by impedances as well. So we'll call this one ZWA. ZWB. ZWC. And our neutral conductor will also have some associated impedance. So let's call it ZN. All right, so in order for this system to be balanced, the following criteria must be met. So let me write that down. So our first criterion is that the magnitude of the phase voltages at the source are equal, meaning that the magnitude of VAN has to be exactly the same as the magnitude of VBN, which needs to be exactly the same as the magnitude of VCN. And we will simplify this and call this VP, where this just means phase voltage, okay? So our magnitude of our phase voltages must be equal in order for this system to be balanced. We also require that there is 120 degrees of phase separation between our sources, meaning that the angle theta BN actually, let me write this in a way that's maybe a little less confusing. So theta BN, which will be the angle of VAN, there's going to be VBN, must equal theta AN minus 120 degrees, where we are assuming here that we have a positive phase sequence and theta CN has to be theta BN minus 120 degrees. If we had a negative phase sequence, we would simply change those minus signs to plus signs, okay? So under these two conditions, our source is considered balanced. And we talked about both of these conditions in our last class meeting. Now, for our transmission line network to be considered balanced, that will require that the impedance ZWA is equal to ZWB is equal to ZWC. And so we might simply just call this ZW. One very important thing to note here is that the neutral conductor impedance does not have to be the same as the transmission line impedance. So I'm going to make a note out here to the side. Zn does not have to be equal to ZW to maintain balance, okay? It doesn't hurt anything if it is, but it typically is not, and I'll explain a little bit why later, okay? And then in order for us to have a balanced three-phase load, our impedances ZYA, ZYB, and ZYC must be identical to each other. And we can call them just ZY for simplicity's sake. Okay? So these are the four criterion that absolutely must be met in order for our system to be considered balanced. And all four of them have to be met concurrently, okay? So the consequences of having a balanced three-phase system can most easily be observed by determining the line currents of our system, where a line current are defined to be simply currents flowing through the transmission lines. So I'm going to define our line currents on our schematic here. So we'll have a line current I lowercase a uppercase a because it's flowing from terminal lowercase a to terminal uppercase a. We'll have a line current IBB. And we'll have a line current ICC. I'm going to define one more down here, which I wouldn't fully consider to be a line current, and I'll explain why a little bit later. And I'm going to call this guy INN. I'm lumping it in with the line currents right now because it is the current flowing through the neutral conductor portion of our transmission line node. Okay. So we are going to do some analysis here. And the first thing that we are going to do is choose a node to be our reference. And so the node that I typically like to choose is the source side neutral. So we are going to consider this to be ground for our analysis that we're about to do here. And it's purely to make the math easy. In truth, a three-phase system doesn't actually have a ground. We have the two neutral conductors and all that kind of good stuff. And outside of the system, the neutral conductor may be tied to ground depending on what is required at the site. But in this case, choosing this node to be ground is purely for making the math less horrifying, okay? So what we're going to do now is we are going to apply Kirchhoff's current law at the load side neutral, okay? And actually, let me write down. Here we had IAA, IBB, and ICC. And now we're going to apply KCL at node capital N, the neutral conductor, or the neutral node on the load side of the system. So effectively, we're just applying KCL at this rightmost node. We can see that a line current IAA flows into that node, a line current IBB flows into that node, a line current ICC flows into that node, and our neutral conductor current INN also flows into that node. So we can say then that IAA plus IBB plus ICC plus INN is equal to 0. Now what we're going to do is use Ohm's law. And we're going to use Ohm's law to represent these four currents in terms of our source voltages using a double subscript notation, okay? So, for instance, the current IAA is simply the voltage drop between these 2 points divided by the total impedance. Well, the voltage drop between those 2 points is VAN minus V capital N lowercase n. This is why we're choosing lowercase n as our reference. Okay. So we would have VAN minus VNN over ZWA plus ZYA plus VBN minus VNN over ZWB plus ZYB. Actually, sorry, these should be capital letters because that's what I've been using. Plus VCN minus VNN over ZWC plus ZYC. And then for our neutral current, the voltage here is simply 0 because it's tied directly to our reference. So we're going to have 0 minus V capital N lowercase n over Zn. Make sure I wrote the Zn. And set this equal to 0. So this is what our generic expression would look like. For a balanced network, let's call this this equation can be simplified. So I'm going to move VNN over Zn to its own side of the equation. So let's put it over here. And then we would have VAN minus VNN over ZW plus ZY for our balanced network. All of our transmission line impedances look the same and all of our load impedances look the same. And we're going to have plus VBN minus VNN over ZW plus ZY plus VCN minus VNN over ZW plus ZY. And now I'm going to do a very small amount of mathematical manipulation here. I'm just going to move all of the VNN terms to the left-hand side. And so what that's going to look like is I will have VNN multiplied by a factor of 1 over Zn plus 3 over ZW plus ZY is equal to VAN plus VBN plus VCN over ZW plus ZY. As a quick aside here, we are going to add VAN, VBN, and VCN together with the understanding that these are balanced source voltages. So over here, okay, let's do it down here. So if our source is balanced, then VAN plus VBN plus VCN looks like VAN plus VAN multiplied by one angle negative 120 degrees, because we know that our B phase should be lagging our A phase by 120 degrees, plus VAN times one angle negative 240 degrees. Or we would have VAN multiplied by one angle 0 degrees plus one angle negative 120 degrees plus one angle negative 240 degrees. So Matthew, or I'm assuming Joshua, yep. One of you gentlemen, throw that factor, one angle 0 plus one angle negative 120 plus one angle negative 240 into a calculator and tell me what you get. Zero, absolutely correct. So if VAN plus VBN plus VCN is equal to 0, then coming back up here, VAN plus VBN plus VCN over ZW plus ZY must also be 0, which in turn means that the quantity VNN has to be 0 volts, because the only way to make the left-hand side of this expression equal to 0, assuming that our impedances are not infinity, effectively, is if VNN is 0. Okay, so this is a very important result. In a balanced three-phase system, the voltage at both of our neutral conductors must be 0. So we can use this result to observe a few things. Our neutral conductor current, INN, is negative VNN over ZN, and this has to be 0. Okay. I'm going to write something out here. In a balanced three-phase system, the voltage drop over Zn and current flowing through Zn must be 0. So what this means is that for a balanced three-phase system, we don't actually need to have a neutral conductor at all. Okay. So for our YY configuration, it would literally behave the exact same way if our neutral conductor was a short circuit, if our neutral conductor was an open circuit, or had any impedance in between those. Okay. We are going to use this a little bit later on, but that's why we can get away with having that three-phase, three-wire system that I introduced at the beginning of class yesterday, where we don't connect our neutrals to each other. In a balanced system, the neutral conductor is entirely unnecessary. We can observe that our line current, IAA, which is defined to be VAN minus VNN over ZWA plus ZYA in its most formal sense. Well, for a balanced three-phase system, this is just going to look like VAN over ZW plus ZY. Our line current IBB in the most formal sense would be VBN minus VNN over ZWB plus ZYB, which is, in a balanced system, simplifies to VBN over ZW plus ZY. And we can take this one step further. Looks like VAN over ZW plus ZY multiplied by a factor of one angle negative 120 degrees, or it's simply IAA times one angle negative 120 degrees. So the magnitude of our line currents are going to be the same, and they are just going to have a phase separation of 120 degrees, just like our voltage source did. I'll formally write down the description for ICC. So we'd have VCN minus VNN over ZWC plus ZYC, which looks like VCN over ZW plus ZY, or IAA times one angle negative 240 degrees. Okay. So for a balanced three-phase system, our line currents are balanced, meaning that they all have the same magnitude, but they have a phase separation of 120 degrees. Now, knowing this about our line currents, what does it tell us about other quantities? So let's scroll back up here. Okay. So give me just a moment. Sorry about that. So if these line currents are balanced, what does that tell us about the phase currents IAN, IBN, and ICN in our load. Well, IAN, IBN, and ICN have to equal our line currents because we just see the impedances in series. So our phase currents must also be balanced. Similarly, our phase currents in our source must also be balanced. So this would be IAN, IBN, and ICN. And since these are just negative R line currents and our line currents are balanced, these phase currents are also balanced. We know that our phase voltages at our source are balanced, but it turns out that our phase voltages sorry, this should be CN, in our loads will also be balanced from Ohm's law. So if the currents have the same magnitude but are 120 degrees out of phase and impedance ZYA, ZYB, and ZYC are literally identical, then the voltage drops across each of these impedances will have the exact same magnitude and they will be 120 degrees out of phase with each other. It could also be shown that our line voltages, VAB, VBC, and also VCA are a balanced set of voltages, and our source side line voltages, VAB, VBC, and VCA are also a balanced set of voltages. So effectively, in a balanced three-phase system, all of our voltages, it doesn't matter if we're talking about line voltages or phase voltages, and all of our currents, it doesn't matter if we're talking about line currents or phase currents, will all have the same magnitude and 120 degrees of phase separation. So that leads us to what I'm going to call the single phase equivalent circuit. Okay. So sorry, I'm getting text messages from a contractor that's at my house and it's distracting me. My apologies. So in a balanced three-phase circuit, or specifically the YY circuit that we just looked at, the voltage drop across the neutral conductor was 0, and the current through the neutral conductor was 0. So that means that we can effectively treat our neutral conductor as a short circuit, regardless of whatever its actual impedance is, even if the impedance of the neutral conductor is infinity or an open circuit. So effectively, we can treat it like a short circuit regardless of whatever is or is not connected there. So from this observation, any balanced three-phase YY network can be broken down into 3 independent single-phase equivalent circuits. So our A-phase equivalent circuit is going to look like this. So this is our voltage VAN, This is going to be our terminal uppercase A. This is going to be our terminal uppercase N. Over here is lowercase n. Between lowercase a and uppercase A, we have our transmission line impedance, ZW. Between uppercase A and uppercase N, we have our load impedance. This is going to be ZY. And then connecting our neutral terminals together will be a short circuit, since we know that the voltage drop across the neutral conductor is 0 and the current flowing through the neutral conductor is 0. We will also have a B-phase equivalent circuit, which will literally be the exact same thing, except our voltage here will be VBN. And then we will have a C-phase equivalent circuit. Sorry, that should be capital C. And using these single phase equivalent circuits, we can determine some quantities extraordinarily easily. Okay? So for example, we can easily determine our line currents, IAA, IBB, and ICC. We can easily determine our phase currents, IAN and IAN, IBN and IBN, and ICN and ICN. We can easily determine our phase voltages. I feel like I'm getting all my colors mixed up, but it'll be okay. VAN, VBN, and VCN. The only thing we can't easily determine here are our line voltages. And the reason why we can't easily determine our line voltages is because we've effectively decoupled this circuit, and so we no longer see the obvious connections between the different terminals of our source and load. And we'll talk about what to do with that in just a moment. So let's work a simple example here, just to illustrate how to use our balanced, or excuse me, our single phase equivalent circuit. So let's say that I have an ABC phase sequence balanced three-phase Y-connected source which supplies power to a balanced Y-connected load we're going to assume that our transmission lines are simply short circuits. The magnitude of the line voltages is 208 volts RMS if the load impedance per phase is ZY is equal to 36 plus J12 ohms. Determine the line currents and phase voltages if theta AN is equal to 0 degrees. If you've looked at the homework sets that I have put up for you all, you have hopefully noticed that all of our three-phase systems are described effectively as word problems like this. Once you work enough of them, you will be comfortable enough to where you could actually just construct your single-phase equivalent circuit from the information that's presented here. But until you get that comfortable, it's probably best for us to draw our three-phase system and then figure out what it is that we okay. So I'm going to draw our system. We're told that we have a YY system because our source is Y connected and our load is Y connected. So here we have our voltage VAN. Here's our voltage VBN. Here is our voltage. Oops. Need to actually draw the voltage source. VCN. And just for the sake of argument, I'm going to throw in a neutral. Doesn't particularly need to be here, but just for completeness' sake, I have my load on the right-hand side. And I know that my source is connected to my load through a transmission line network made up of short circuits. We are asked to determine the value for our line currents, IAA, IBB, and ICC. We are asked to determine the value of our phase voltages. So I'm going to do that over here. Technically, we're going to have to figure out what V lowercase a and V lowercase bn and V lowercase cn are as well, because we were not given those pieces of information. And those are also phase voltages. What we were told is that the magnitude of our line voltages, so I'm just going to put one line voltage right here. We were told that the magnitude of our line voltage, VAB, was 208 volts RMS, and it actually wasn't specified, so that could also be voltage VAB like so, but it doesn't particularly matter in this case because those two voltages are connected by short circuit, so they have to be the exact same thing. So it literally doesn't matter if we consider these to be line voltages at the source or line voltages at the load. If it were to matter, I would have told you the magnitude of the line voltage at the source were blah, 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 or the magnitude of the line voltage at the load were yada, yada, yada. So that's one piece of information. We were told that the impedance ZY is 36 plus J12 ohms. And we are told that theta AN was equal to 0 degrees. Okay. So I'm going to draw our single phase equivalent circuit, and then we're going to figure out what information we need to get before we can really put it into practice. So let's just look at the A phase. We are asked for this quantity. I'm using blue here, yeah. And we are asked to solve for this quantity and this quantity. So we can see right off the bat that our phase voltages VAN and the V uppercase AN and V lowercase AN are literally identical. But in order to apply our single phase equivalent circuit, we would need to know what one of those two things are. Okay. Another thing that we can observe, hopefully very easily here, is that our line current IAA is just going to be VAN over ZY. So I am of the opinion that it is absolutely critical for us to solve for this quantity v lowercase a lowercase n. Okay. So I'm going to scroll back up here to our original circuit, and I'm going to talk about how we might go about doing that. So what I'm going to do is I'm going to write a Kirchhoff's voltage law equation around this loop. Okay. So that equation, I'll tuck it in down here, I think, tells me that negative VAN plus VAB plus VBN is equal to 0. Now I know that VBN and VAN are related, okay? So I'm gonna algebraically rearrange this guy a little bit. I can say that my voltage VAB is simply VAN minus VBN, which is the same as VAN times 1 angle 0 degrees minus 1 angle negative 120 degrees, or VAN multiplied by a factor of the square root of 3 angle positive 30 degrees. By all means, throw 1 angle 0 minus 1 angle negative 120 in your calculator and prove to yourself that that is 3 angle 30 degrees. So from this, the magnitude of VAB has to be the magnitude of VAN multiplied by a factor of square root of 3, and therefore the magnitude of VAN is the magnitude of VAB over the square root of 3, which will come out to be 120.089 volts RMS. We are given the phase angle for VAN right here. And so now we're effectively ready to solve for things. Okay. So this is just 120.089 angle 0 degrees volts RMS. And then if we substitute that in and divide by ZY, our line current IAA looks like 3.165 angle negative 18.435 degrees amps RMS. So what we've solved for here is the phase voltages and the line currents in our A phase. But our problem statement did not specify what phase. So typically that means that we want all phases. We don't actually have to do any more circuit analysis whatsoever, right? And so what I mean by that is we know that VBN will be equal to VBN, and this is just going to be VAN times 1 angle negative 120 degrees. So VBN is going to be 120.089 angle negative 120 degrees volts RMS. And similarly, VCN will be equal to V capital CN, which is just VAN times 1 angle negative 240 degrees, which is 120.089 angle negative 240 volts RMS. Similarly, our line current IBB is just IAA times 1 angle negative 120 degrees. So that's going to be 3.165 angle negative 138.435 degrees amps RMS. And our line current ICC is IAA times 1 angle negative 240 degrees, or 3.165 angle negative 258.435 degrees amps RMS. So once we can apply one of our single phase equivalent circuits, we no longer have to do any other analysis whatsoever, because we know that for a balanced system, all of our voltages and currents are going to have the same magnitudes, about 120 degrees of phase separation. We can simply just shift the angles by 120 and 240 degrees to get what's going on in the B and C phases respectively. All right, so this is the analysis of a YY system. And it is, in my opinion, and hopefully yours as well, a pretty straightforward process when utilizing the single phase equivalent circuit. What we are going to talk about in our next class meeting is a bunch of transformations that we can use to make any three-phase balanced circuit. So it doesn't matter if it's a delta Y, a Y delta, or a delta delta system, but we can make any three-phase balanced three-phase system look like a YY system so that we can use our single phase equivalent circuit using these transformations. So that's what we're going to talk about next class meeting. And then we're going to work some example problems before we get into our power relationships. All right. Does anybody have any questions for me before we knock off for this morning?